But really, it was just simplifying his yeah, simplifying his whole setup because he was in a house with multiple floors and stairs and a yard to manage, and we got him in like a 55 and up community, so he doesn't have to do anything. Let's see, should be. Let me see what I'm getting. Can you talk in the mic?
Yeah, can you hear
Okay.
me?
Yeah, yeah, there we go. I was just trying to find levels to make sure I'm capturing your audio,
Okay.
but we're good.
Yeah, if I'm quiet at some point, do let me know, cause
Well, you had no audio, and that's why I was like, I had to adjust it to pick up the audio for my
yeah,
headphones or whatever.
mm,
Um,
man, I got into that oh my posh rabbit hole, but now my terminal looks so good, so happy about
nice, dude. Nice. You let me know when you're ready to start, and I'll cut this thing over.
it. Cut, you mean?
Like it's like on a loading screen, I think. Maybe
Oh,
they
okay.
can
I,
hear
got- I got
us.
the notification already on Twitch that you're live.
Yeah, yeah. That's I put it on like a
I see what you mean. Like soon. Yeah.
yeah, yeah,
Dude,
yeah.
you're
That's
you're
I
becoming
put it
a
on like a.
streaming whiz, man. I see what you mean. Like, is this built in on Twitch or did you come up with that?
No, I just created that, and I'm pretty sure they
Yeah,
can hear us on the other side. We'll find out. But
that's
yeah,
cool.
cool. Let's
Cool.
cut over to where they can see us as well. They being ooh, we've got two viewers. Nice, nice. Welcome back to Programming Bitcoin with Gary and Pleb Lira, where we do things that we have no idea how they work or what they're doing, but we're learning. Uh, yes, yes. That was. Well, I think did we even get to? Did we get to multiplication? We did. We did. Okay, we did the power of exponentials. We didn't do division yet. Yeah, we did not do division yet. Uh oh. I've got a volume switch that I just hit on accident, so you were quiet. You're sensing that Jimmy what? Yeah, I think yeah, I mean a lot of these it seemed like a lot of these formulas when I was because I was reading through chapter 2 as well. I just kind of like read through it. I didn't really do anything. I just read it. Um, once you have the proofs, right? The proofs, you make. I don't want to say they're not assumptions. They're statements or facts or whatever. Where it's like, okay, this function equals this other function, right? By whatever property that is being applied to it. And I think you do kind of have to just accept some of those as the truth, at least when you're at our level of understanding of all this math and stuff. Because a lot of this, some of this was like a little bit over my head. Um,
Go back interacting with you. Oh, this is where it applies, and this is more digested,
Yeah, yeah, yeah.
so like everything becomes simpler.
Yeah, it was definitely interesting. I went and watched a couple of YouTube videos though on the whole elliptic curve, and there's like some guy that like was using like a cigarette box as a straight edge to like do his elliptic curve, like the addition or whatever, where you how do you explain it? It's you find the two. Shoot, now I can't remember what it is. It's like you
The
find the 2 points,
intersections.
yeah, the intersections, and then like the answer is like the inverse. You find the intersections, and you find the
Yeah,
third point on the curve, and then the answer is that third point, but like inversed over the x-axis.
exactly. Yeah.
So that was super interesting.
Yes, that's good to hear. Like looked for some other sources of info on that.
Yeah, because everybody explains it differently, and I mean when you're reading something, it's you can only I don't know. My reading comprehension probably could use some improvement then. But let's do
Yeah.
division. Did you
Yes.
do the
Yes.
division in Python?
Mm-hmm.
Okay.
Yeah, and I guess yeah, that's why I was thinking when you mentioned division, like I couldn't do everything that he explained in division, but I got like the gist that when you're dividing, you're basically multiplying by the power of -2, by the power of the prime -2.
Yeah,
You,
I remember
you
that.
remember that, right?
Yeah, 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 yeah. I remember, and it's. Oh man, I can't remember the reason for it. Um, to
Yeah,
multiplication.
like the two divided by 7 at the bottom of your page there.
Yeah. In the
Time- Yeah.
the exponent, that is the order of the right
Hmm.
order of the finite field.
The order of the finite field -2. And that -2 is arbitrary. It's always -2.
Well, it's -2 because of this Fermat's little theorem or whatever.
Hmm.
Um, and yeah, I tried to understand this one too. It's just I read it a few times, and it's just I just have to like press the I believe button.
Exactly. It's hard to verify those kind of
Well,
instructions.
it is, but
Yeah.
I was also thinking that I wonder like maybe we could write a proof as like a test. You know what I mean?
Hmm.
I don't know if that'd be helpful or not, but um, like taking this and like actually plugging in numbers and doing like an assertion on like that it's equal, right?
Hmm.
Um,
Yeah, let's do that. All we have to do is pick prime.
yeah, so it'd be
That's it, right? Yeah, because
n-
n is gonna be.
19.
We have to pick an n as well. Yeah.
I don't remember what the explanation. Oh, exclamation point is factorial. Okay.
Hmm. I never searched for how to do factorial in Python. It's probably a method that is,
Let's
and
see,
there's
Rust.
probably one in Rust. Yeah.
Probably. Play the factorial. It's great. Well, factorial would just be um, this might not be the right way to do this, but it'd be what 17. This is kind of brute forcing it, but There's probably a much more elegant way to do this. Right, this is factorial, right? This is like, that's what you end up doing all the way down to 1.
Mm-hmm. You want to put a parenthesis in the subtraction, yeah, or just make it 18.
That's true. Well, I'll leave it like this because that was closer to what it was. And then mod 19, and we need to assert. So that is equal to the same thing again. Times n. What are we plugging in as n though?
N is, I guess, any number, because it's gonna modulo afterwards. So any number is gonna be the same thing according to the exercise before that.
Yeah. And it's pow 19 minus 1, and then mod 19. And then, like, that assertion should be true. I see what's going on here. We need parentheses right here. That's so ugly with all those numbers. I hate it. Oh well. What is this complaint right here? Oh, semicolon, okay. Where's this complaining at? Semicolon? Why does that need a semicolon? Oh, okay. I forgot parentheses at the beginning here. Unclosed delimiter. Oh, we didn't close the entire assertion. What did we miss here? Oh, excuse me. This is what I get for having just way too many. Oh, we don't need that there. Okay. Alright, there we go. Parentheses are probably like one of the stickiest things.
What is the 3 times pow? Why is 3 there specifically?
3 is the n. It's just the any number, right? So I just picked 3.
Okay. So instead of doing like putting the 3 everywhere, you just put it at the end. It's the same thing.
Yeah. So is this? Uh-oh. We got errors. Oh, we got an integer overflow. See if it works at 64. Test failed. So it did fail. Wonder what we did wrong. It's also yelling at us for this being not snake case. So we did that now. Oh, come on. It's not gonna... So I wonder why it failed. I wonder if we can print each of these numbers. Yeah.
No. See if I do it different.
Oh, okay. It's basically saying that we need to give it a string literal. What is this? Oh, okay. We need to find a type. Okay, let's run this again and see what happens. Oh. So it's too big of a number. Let's use a smaller prime then maybe. Unless there's a bigger.
He's calculating it in 32 bits.
No, it's doing 64-bit. Oh, it is.
Yeah. Maybe the first one. Yeah, that is the first one.
Yeah. So maybe if we define one of these as do unsigned 64.
Unsigned gives you more.
Yeah. That did not work. Attempt to multiply with overflow. Okay, so yeah, the number's just too big right now.
Okay.
Well, I wonder if that's going to be an issue too for future stuff. You know what I mean?
Yeah, I think that's why he uses the Python power function that modulus after each application. It might be an equivalent in Rust.
Yeah. Let's modulo exponent. Oh, we already looked it up. So I wonder if we're going to get issues when we go to do division with our...
Yeah, because it does get some pretty big numbers.
Yeah. So let's try... Because you have to do the exponential to get up there. Interesting. Well, what are the Rust? I wonder what's bigger. Like, is there a bigger type that we don't get an overflow? Because we need to... How did you code it in Python?
Are these big, or you mean this division, or the division?
The division.
As well? Yeah, let me go there. You want to invite me to the live share?
Yes. Just a moment. Alrighty, there we go. So you are invited. Oh, it's the power to p minus 2, right? That's the...
Multiply by the power of p minus 2.
Right.
Multiply by the divisor to the power of prime minus 2.
Right. Okay. Oh, so I wonder, let's see. Okay, so right hand side, it would be, what's the term for that? That's the divisor, right? The... Oh man, I'm trying to remember the names.
Divisor is the one on the top, and dividend in the bottom. Right?
Dividends on the bottom?
No, the other way around.
Okay.
Dividend is the one you start with. Divisor is what you divide by.
Gotcha.
Which makes sense, right? In terms of the language.
So with 2... Which we'll just ignore this for now. We'll go back to doing division works. So we're asserting here that 3 equals, well, we need our 2 field elements. And so we've got 2, and this is 19. It's the order of 19. And then we have 7. Whoops. Also the order 19. And then we should, so 3. So if it's order of 19, 2 divided by 7 is 3 with this modulo division. So this would be A divided by B. Yeah, that's going to fail. So that's just because we don't have a return type. Okay, cool. So I guess the first thing is we need to do this check to make sure that they're both of the same order.
Yes.
And then, yeah, we calculate the new number. And so it would be the self, that number, which in this case would be 2, times, and then 7 to the 17th power, right?
Mm-hmm.
And the 17th power, but the 17th power is just minus 2. The prime minus 2. And then we take all of that again and modulo it by 19.
Yes.
Okay. And in this case, 19 is the prime, or the order of... So the number times the dividend times the divisor raised to the power of order minus 2 mod order.
Mod order, yes.
Okay. field element that has a new number and self.prime.
Yeah, and in Python, let me show you here.
Sure, yeah.
This is the line. It's just a little. You scroll down a couple lines, you can see. Yeah.
Right here?
So the new num for you, self num, right? Thanks.
Yep.
So this is the pow function in Python, which is really amazing. So how this works, it has 3 parameters. The number you're
Raising.
Powering, raising by.
Yeah.
Thank you. Actually, what is this?
I think you have extra code here, right? At the end? Like you wouldn't need this last mod.
Yeah, because it's modding by this already. Where did they put it here?
Is this from the notebook or whatever that you're referring to?
Yeah. Times.
Do you have tests that make this work or no?
Yeah. Okay, so you're multiplying. So this is the self, right? There's a multiplication here, which you also have.
Yep.
Times the other number, and that other number is raised to the prime minus 2. Minus 2. And this third parameter here is the modulo for the pow function, which is it modulos after each time it's raised by. So raised by 17 here in our example with the 19 order. It raises once, it modulus. Raises one more time, modulus. So it's always going back and forth. The number never grows to be that big. But it's moduloing after each multiplication.
What did they call? Did they have a name for that they referred to it as?
I don't know. Let me find that in the book. Yeah, because it's so convenient. Probably very much less taxing in resources.
Yeah. Oh, I also started to go look at. I was looking up like elliptic curve cryptography, like somebody else wrote the code already, libraries and stuff like that. So. Here's one. Mod exponent. So here's a crate that does it, apparently.
Nice.
So maybe we should add that crate then to the...
Crate in Rust is kind of like a method.
It's like a package. So somebody wrote this already. And then we can go check out like the source code for it if we wanted to.
Oh, here, so this is on page 14.
Of the book?
Let's go to page 14 in the book. Yeah, like right before exercise 8, he explains that part about the mod done after each round of multiplication. It's on a different page. It's right before exercise 8.
Right before... Oh, here it is.
Oh, sorry, 15, yeah.
It's a relatively expensive calculation as exponentiation grows very fast. Division is the most expensive operation for that reason. To lessen expense, we use the pow function in Python, which does exponentiation. Okay.
If you read the last sentence, we get the same result, but it's so faster because the modulo function is done after each round of multiplication.
Oh.
Pretty clever, yeah. The exponentiation.
So I'm pretty sure that's what this does. So let's use this crate then.
Right. Yeah.
Um,
Open that crate.
right. Let's add it. Cargo.toml. Mod exponent.
You have to do it like a pip install or of sorts, or these are all already.
No, it does it when the code compiles.
Oh, right, not
I
interface.
believe so. Yeah, I believe it does. So in this case, we don't need any of this, right? It would just be, oh, not mod pow, it's mod exponent. I mean, maybe we do need to do a cargo install. Probably right.
Yeah.
Okay, so it did yell at me. All right, it compiled that. See, okay, so it did the thing. There it is. And we give it the base, the exponent. So the base would be the other one, the divisor dot number. The exponent is self dot prime minus 2. And the modulo is self dot prime. All right, there we go. So that looks more similar to your Python method here. See if it works. Well, what's going on here? Cannot compare integer. Oh, okay. Now, does this result in a field, right? That's not like what was it, the exponent? Do the exponentials, like when you divide one field element by the other, you get a field element, correct? Okay. So that's the problem that it's complaining about here then. Is because this is 3 is not a field element. Not found in this scope. What? 83. Oh, whoops. It's not other. Unused. Alright. I just want this to stop complaining about things. So failed.
And this is supposed to be 3.
Is it a... I don't remember reading that if it's a... Is it supposed to be 3?
That's a good question.
Yeah.
Well, try modding the whole thing by prime at the end.
Again?
Yeah, like the full result before the semicolon. I think that might be what we're missing. Passed, right? Yeah.
This is why I have you here. Now that
It
make
looks
why so.
redundant. 'Cause
Oh, okay.
I,
Okay. All right. I get it now. So it's because like this right here is handled by that modular exponential,
the one that
but
you
you
just
still have to
multiplied.
mod that modular exponential at the end, like one final time.
Yes, the one that's being multiplied by the
Yeah.
dividend.
Right. 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 Yeah, because
Mm.
the dividend times whatever this number is probably going to be um, bigger than the order,
Mm-hmm.
and so we mod it one last time, and now we're in that finite field because we're within that order.
Exactly. Yeah.
Cool, 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 cool.
Nice.
Nice, dude. Well, that was good. All right. Exercise 9 done. So what is this? What is this redefining experimentation?
I think what he's covering, so exponentiation also works for negative exponentiation.
Yeah.
What he's gonna do, yeah.
Ooh. Excuse me. So I wonder if ours already works with negative. Probably not.
And
Let's see here. 7 and 13. What was the change that we need that needed to happen for it to accept the negatives?
it's like if you look where he's defining the class, he adds that while loop. And he basically, yeah, his all n equals 0, so n is the exponent. So he adds the self prime minus 1 to the exponent until the exponent is greater than 0. And then he runs the regular Powell function.
Huh.
Which he explains above, but I didn't. Yeah,
Well, I'm
we
thinking
need to
I'm
go
thinking
with
about it
him
like
and
on a number line of sorts, right? So it's like you have this window of you have these windows and numbers, and so say we're dealing with order of 19, and it's
Mhm.
-3. Well, if we take that, if 19 minus 1 or whatever is going to be 18, and we add that to -3, now we're at a positive 15. And so the whole, all of this modulo stuff is like you're doing something to get to a positive number within that, like, within that set, within that, within that order, like, right?
That order, yeah.
And so this seems like it's along the same sort of process, that even if you have a negative that's larger than the order, right? So like even if we had um, like, I don't know, like -52, right? And that's for something of order 19. So you would add 50 -52 um, plus 18, which will just
34, I think.
probably. Oh, it's freezing up on me. Yeah, it sounds like it's 34. That makes sense.
The,
Because 2
the
from
while
18
loop,
to 16. And so the next one, yeah, the next one would be plus 17, right?
34 is 18. Oh no, it's always 18, so it just keeps adding self prime
Oh yeah, yeah, yeah.
-1. It will be plus 18 again.
And so that would,
Minus 16.
and then once we're here, now we have a number that's within our field, our finite field.
Mm-hmm. Yeah.
It's the same kind of trend, right? Like because all these additions and multiplications and everything, like we're modding everything to get within that field. Um, to and so it would just make sense that this is also happening, I guess.
Mm-hmm. And we're going, yeah, entire cycles, which are prime -1. Instead of going arbitrary numbers, the cycles we're going like a whole, going around the whole clock with
Yeah, yeah, yeah,
the
yeah, yeah, yeah.
yeah.
Yeah, the clock.
You can't go like just, oh, I'm just gonna go half. No, you have to go full rounds around it.
Yeah, yeah, yeah.
Yeah, that's, yeah, very interesting.
Cryptography is crazy stuff.
Yeah, I can't wait like to see it, where how this is actually gonna land into
Mm-hmm.
cryptography.
Oh, we're doing -3. Oh, can't do it because we're using the wrong. Let's just rename this real quick.
Rust, they like snake case, like in Python.
Yeah. Yep. Yep. And it yells at you. The compiler. Well, you can turn that off if you really want to, but yeah, it will suggest that you do not. So we need not a use
Camel case.
size. What are the Rust primitives? I missed a word there. I size. Oops. So I just allows us to have a negative there. Oh, interesting. Look at that, because it doesn't. The exponential function doesn't
Right.
like doesn't like an I size. So like it doesn't. The Rust doesn't want it to have a negative number.
The gecko. Which I think that might be the case with the Python as well. Or not. No, maybe it doesn't say.
I have no idea. Yeah.
Yeah.
So we have to change. There's probably a way to do this a little more elegantly, but we have to do. We have to make it mutable because we're going to be changing the exponent.
Mm.
And so self dot prime -1.
Strongly typed, huh?
Yep. And it's not going to like
In
this
Python.
either because we are interesting. So how do we make this work? Because we're comparing I size.
Self prime is U size.
Mm-hmm.
Oh, wow.
But I think we can cast it. Yeah, so there's this. It's like this into function will just say like, hey, just convert this, like try to cast this into whatever whatever type that we need it to be. So in this case, it tries to make it into an I size.
Mm.
Um,
You don't even have to specify it. It just picks it up from what you're giving it to.
Mm-hmm. I mean, we could, like, you can specify, um, pretty sure, I can't remember how to, oh, there it is, to usize.
Mm.
So we could do that, we could explicitly,
You wouldn't be to usize and then you put the expression inside the parentheses.
no, it'd be two, I'm sorry,
No.
it'd be two I size, right?
Nice. Nice.
Oh, but the,
You know what I mean?
um, so what happens is, so there's this concept in Rust. So this iSize returns an option of iSize, and this option type is how Rust sort of avoids nulls, right, or the none in Python,
Mm-hmm.
where it gives you this option where you sort of have to explicitly handle the result of that option. Which is a very easy way to do that is just unwrap it. It's called unwrapping, where you just unwrap the value, and if it fails or has an error, the whole program just crashes. It panics.
Mm-hmm.
And I'm pretty sure that this into function just like is a shorthand for just like I want you to make it what it needs to be, and just like get the value out of there. And if you fail, just panic, which means that the
Nice.
application will crash.
Mm-hmm.
So anyway, we've got that now, and then we can take exponent now, but we'll need to cast it to a usize, which again we can do into as well, or maybe not. So we can't do that. I don't know exactly why. And again, this is kind of where my Rust knowledge is seemingly lacking. But we should be able to do this. What is this doing here? Why is it not liking that? Try using a fully qualified path to specify the type. Okay, so it doesn't like us using the usizer. Or it doesn't like us using the into. And again, we'll just unwrap it. Which is this sort of like a way of saying we're not going to handle this right now. So just make it work. Cool. So I guess let's run it and hope it works. We added our new -3 here based on the example in the book. All right, hey, that worked. I'm sure there's a...
3.
What's
Then
that?
it was -3, so you added 18 to make it
15.
positive 15.
Yep.
And then it calculated the exponential. So theoretically, or practically as well, if you make the same calculation but you make it to the power of 15, you should also pass the test, right?
What do you mean? Like change the prime number?
Change the exponential to 15.
Oh.
See if the test passes.
Okay, yeah.
Or positive 15, right?
I mean, I think either or will work. No, positive 15 didn't work. Negative 15 did. Oh, hey, wait, yeah. Oh, wow, okay. So, interesting. So,
Oh, sorry. We're in 13, right? We're in order of 13, so
yeah.
it would be 10, right? Or no, 9. tripping here. Sorry. So it would be -3
Min
plus order -1.
plus 12. So -3 plus 12.
That's 9.
Yeah. So positive 9, which should be the same, right?
Mm-hmm.
Passed.
Okay.
But negative 15 also gave us the right answer. It also worked.
Ah, because yeah. Oh, what a coincidence. Because yeah, -15 plus 12 is
Is
-3.
-3. Yeah, yeah, yeah.
We're in the same cycle.
Oh, wow. Huh. You know that kind of oh, interesting. I wonder if that I'm thinking about like the elliptical the curve, right? And how it's like a mirror
Mm-hmm.
and
And the x-axis.
yeah. Anyway, I don't want to overthink it.
And
This
how
is
it relates to cycling
yeah, yeah, yeah,
in
yeah,
many
yeah.
ways.
Yeah, that's what I was kind of getting to. Um, this is kind of crazy the way that all this math works, though.
Yeah, it's so abstract.
Mm-hmm.
Like, yeah, when we're looking at the elliptical curve, like point addition, you're not really adding anything. Right? It's not an addition. Like one plus one, 2 plus 2, right? It's like this abstract addition.
Oh, they make it even better though here.
Hmm. Ah, like a modulo. Ah, modulo on the exponent. Yeah, that makes sense.
Which we just talked about actually. Like we just talked about how that subtraction or the addition of the order -1 really just ends up becoming a modulo itself.
Yeah,
You know what I mean?
right. Yeah, exactly.
This is so cool. Like I mean I've always been decent at math, but I've never like this is kind of interesting. I don't I guess I
Yeah.
never assumed it would work this way. So this just simplifies to we just mod it.
Ah, so you don't have to do all the type conversions and everything.
No, yeah.
You still have to do some of it.
And I don't have to make it. I do have to. Oh yeah, I will have to do some of it because this we still need to be able to have a negative exponent.
Mm.
Um, oops. We can actually define this as a U size, and we can wrap this whole thing. It's getting real ugly looking. But we can wrap the whole thing and then cast it back to a U size.
Because modulo always will be positive.
What do you mean?
Yeah, like I'm saying, like yeah, instead of adding prime -1, you just modulo it, and it's the equivalent of just adding prime -1.
Over and over and over again until you get a positive number.
Yeah, it's
Yeah,
the same
yeah,
thing. Modulos are always positive. Yeah.
yeah. That's funny that we talked about it though, and then it was like, oh, you just mod it, and we kind
Yeah.
of, yeah, huh. That's it. We're done. Chapter 2's done.
Yes. Chapter 1, really. We're getting to. Chapter. I think this is 1. Now we're getting to 2, which is
You're right.
elliptical
You're
curve.
right. Right. Yeah, yeah. I'm sorry. I saw chapter. It said chapter 3 here.
Uh,
Um,
elliptic curve.
we turn next to the other mathematical component we need for. Oh, okay, so we're gonna learn the elliptic curves next. Let's commit this up. Chapter 1 done.
I like that you have your panel on the right. My panel's on the left side. I don't know why. I
I
guess it's
like
the default.
yeah, it's the default, but when I'm reading something, because read left to right, if it's on the left hand side, it moves what you're reading. So I just yeah, you can change it.
When, oh, I see. Like if you expand the panel, then everything shifts with it.
Right.
Is this what you're saying?
Yeah, yeah, yeah.
Good
And
point.
so your visual, like I look at the same spot on the screen no matter what, but if mine's on the left, when I open it up, now I have to look at a different spot on the screen.
Oh,
I don't
I
know.
like that.
It
Yeah.
might not make sense,
I like that.
but that's why I did it.
No, yeah, it is. Yeah. I think about that a lot, having to relocate your point of vision.
Yeah,
But
yeah, yeah.
it takes a lot of time, yeah, if it happens all the time. Well, maybe I'm gonna have my bar on the right side next time we meet.
Yeah, go for it. Yeah, I mean, VS Code has a lot of customization options. So, uh,
It's crazy, yeah. So many settings.
so elliptic curves.
Okay.
It boils down to what basically this, and then specifically, it goes through a lot of like these linear equations. Um,
hmm
talks about all kinds of them.
Yeah, what I liked about like relating elliptic curves with the finite fields is that in the finite field we have the order, right? The order is kind of like your field where your your court, right? Is the court where you're playing.
Okay, yeah, yeah, yeah.
And in the elliptic curve is A and B. Those two numbers, if they're not the same, you can't really do anything between the points in the curve. So A and B always have to be the same, so the points can talk between each other.
Yeah, 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 yeah. And that
Like the operations
defines
in
and that defines the curve type. And that
that
goes into
defines the
it.
curve type. That's right.
Yeah, it goes into us here where it like there's a disjointed curve. Um,
Yeah.
uh, not this one. There's another good example. Oh yeah, so in Bitcoin, A is always 0, and B is 7,
hmm
and so you get this number. I was actually thinking that I want to get this and print it on a T-shirt
No, nice.
to wear around,
That's
like some like real nerdy, you know, signaling to somebody. Like I feel like that'd be really good OPSEC
sure.
because if anybody sees it and understands what it means, it's like okay, they know. But
You
just
know,
general people will be like, oh, he's a math nerd.
yeah. I like that. It's like super 4D chess.
Yeah, 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 yeah. And then this specific curve, like this is Bitcoin here, right? Like this is. I think I even posted a Twitter. I was like, what is this? Wrong answers only. Um,
This is good for a T-shirt as well, right? Yeah, we
yeah,
did the two things.
yeah, 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 yeah.
Nice. With Jimmy's hat on top. Then you go.
Put the hat on top of the curve.
Yeah. That's it.
Did you get into coding this point class?
I did. Yeah. I
Okay.
was basically, yeah, following the prompts,
Yeah. All right.
but I could definitely go over it again.
Well, let's do it in Rust.
hmm
Programming Bitcoin in Rust, right?
Yeah.
Uh, point. Point seems so generic, but we'll use it. Um, we're not interested in the curve itself, but specific points on the curve. Okay. All right. So we need to find a struct. that will be our point. And what are the fields we have? So we have an X. We'll just say, it can't be U size. I think we'll have to go with I size. With Y, because it could be negative, right?
Points can be negative, yeah. You mean like the X and the Y?
Yeah. Okay. And then A and B, which those are the constants. Which I wonder does it get to some point where you hard code in the Bitcoin constants of 0 and 7?
All the time, like all of the examples, they're always using 0 and 7.
Okay.
A and B.
Yeah. Okay, cool. And then we can create an implementation for point where we create a new function where we take in an X, a Y, an A, and a B. And we'll be returning a point. So we need to check though. So what is this? Y power?
Implementation is kind of the self, the under self, or those in Python. Like the
So
init, right?
the self is just because it's a whenever you create a new point in Python, this init function will be called. In Rust, because we don't have this sort of init or constructor function, we define it ourselves. We did a very similar thing with the field element, right? Where we have this new function that returns a field element, and so we're doing the same thing with point. And then we need to do what is it? X to the power of 3 plus A times X plus B. Oh, we need to find the types of all these.
It doesn't derive automatically from your structure on top.
No, because it's a function, right? Like it's ignorant of the struct itself. Yeah, I don't know how else to describe that.
Interesting, yeah. Because if it being a strongly typed language, I would expect like once you define it, it's defined. But
well, we define the struct, right? And it's the structure of the point itself. But this new function knows that it's a part of the point struct. Like it knows that it's a function available on this point. But what it doesn't know, and we haven't referenced the struct point at all. So we need to tell the method parameters what types to use, because we could create a method on here that's new that could just be anything, right? Like it's not
even though they both share the point name, it could be unrelated.
Right, because we could call this is just creating a function for point. This is not like I said, that's where the whole like init function for Python classes or like constructors in other languages, Rust doesn't really have that concept. So you just see you'll see a lot of people creating their own sort of constructor methods, but because the language doesn't have the language doesn't have the idea of a constructor or an init method, it doesn't like auto sense those sort of things as far as the typing goes.
Nice. Okay.
And I think we were just panicking if it, yeah. Yep. And what is it? X and Y. Cool.
You know what it's doing right in this if statement.
I'm sorry?
You know what's happening in this if statement here. It's basically
Oh,
running this equation, right?
yeah, yeah, yeah.
Seeing if it's actually equal to zero or whichever, whatever number.
Yeah, it's equal to it's
The two-sided,
validating
yeah.
that this is in fact an elliptic curve and not some other point. It's validating that
Yeah,
it is a point on an elliptic curve as defined by
yes.
A and B.
Yeah, the curve defines the A and B define the curve. Yeah, exactly.
Yeah. Yeah, A and B defines a curve and then this first check is saying making sure that this point is on the curve.
Mm-hmm.
And then we can do we need numpy here.
As a coder, this is something you do all the time. Like you're just going back to other projects, other files, and copy and pasting bits of code, right?
Tons. Yeah. It's
Right.
it's interesting. They make a joke that like software development is a lot of just looking things up on Stack Overflow and then pasting them in like changing a couple things. Um,
And that's kind of that's very true, right? Very real.
yeah, that's definitely real if it's something that you've never done before. The nice thing about programming in software is once you have the patterns established, like once you know a while loop or a loop in general, once you have a loop and you understand like the properties of that loop or of a loop in general, or that you can continue to skip over it, right? Or like to break out of loop or use the break command to like kind of get out of loop and stuff like that. Like that applies in almost every language, right? Because it is a programming primitive that applies, right? And so once you have that concept, and then you expand that concept out to all these other patterns, right? So like in my day to day, I work with Java, and in Java, there's like patterns for certain things, and the way Java works. But it's like writing, database access in Java is not going to be super different at a fundamental layer than like database access in Python, right? Because they still ultimately have to access the database as the database defines. And so it's like all these patterns are just it's just where the squiggly braces go is what it comes down to. That's what I like to say is like language doesn't matter, it just tells you where the squiggly braces go. Um,
Nice. I like that.
yeah. I think I
And
can
then
do
you're like going to Stack Overflow like to actually yeah see where the squiggly braces go basically.
well the
Like you
stack
do the right you search. Knowing what to search for sometimes is more important even.
right, yeah, yeah. I would agree with that for sure. Knowing what to search for. Knowing the
Hmm.
terms of what you're trying to accomplish is important to understand. And that sometimes that's the hardest part because you're like you have this concept in your head and you're like I don't know what this is called, and that was one of the biggest like learning curves of getting up to speed on software development.
Hmm.
All right, cool. We've got a new function, and then they defined equality. That's pretty simple. It just checks to make sure everything is the same. which I think, yeah, so we did this. We had to implement partial equal. Which is, that's basically the same check that we did before.
Partial equal would be same curve, different point. Or
No, partial equal. So the partial equal thing, it's like it's a Rust thing for
okay.
if we want to do a point equals point, right? This is the way you do it. I lack the knowledge to explain it. I just know that it has to be this way. And maybe it doesn't have to. Hey, if you're in the chat and you know Rust, please let us know.
Raise your hand.
Yeah, raise your hand, please. Okay, let's. This is pretty straightforward though, so jam this out and be done with it. Cool. Yep, check the points on the curve, and they just have to have the same curve and their same coordinates. So now we can create some tests to validate our code. And we write tests like this. Beep, beep, beep.
Good luck finding points in this curve.
What do you mean?
I was trying to create examples of my own. Like, I just want to create a point.
Oh, really?
To use for comparison. I have no clue where the points are.
Oh, wow.
Maybe there is a way to build. Maybe inputting the X and you can get a few different Y's, you know.
Probably.
I think it supplies us with a few possible points. Yeah, I guess if you fix one of the coordinates for the points, then you can find the other one. Yeah, that's it. -1 is definitely.
I'm just going off the examples here in the book. Oh, this is where we can what's it called? Assert. I thought there's a way to assert panics. Let me see what it is.
Try on Python. Like if there's an error, it keeps going or something like that.
No, here it is. Assert panic. Is a crate for that? There's can't. Come on. There's got to be a way to. Huh. Yeah, I guess we can't assert panic. It's weird. Here we go. How do I write a Rust unit test that ensures that a panic has occurred? Should panic. Ah, okay. And it's this little decorator looking thing. Should panic. And that's this guy. Whoops. And this should panic. let's comment this out and just make sure this panics. Uh-oh. Unclosed
Not
deliver.
the kind of panic you expect.
No, it wasn't. We just forgot to. We forgot the curly brace.
There we go. Squiggly lines.
Hey, it passed. All right, cool.
So if it passed, it means it panicked.
Correct.
It's
Yes.
kind of like
It failed. It passed. It
Yeah.
failed, so we passed. Um,
The squiggly line. Do you mean just to be sure the
curly.
tilde or the curly
I'm
brace?
sorry, the
The
curly
tilde
brace.
is-
Yeah, the curly brace. Either or, right? Maybe there's a tilde one. You know, some language out there that uses tildes.
Yeah.
Depends on the programming language. Sometimes there are no
It's pretty
squiggly lines.
fun. I was watching this video the other day talking about unusual languages. There's like a language that uses emojis for statements.
Yeah, there's like a rock star language or something like that.
Rockstar language. Okay.
Yeah, I've not. I've only heard about it. So this, I mean, we just A equals B, right? Like that's it. This should just work too. Cool. Passed.
Fast, okay.
Nice.
And if you try to create that D2 in the book, it should give you an error.
I'm sorry, say that again?
The B2, 1, 1 minus 2 should give you an error because it's not on the curve.
That was this one. That
You
was
already did it.
the panic.
okay,
Yeah.
That was the failed pass or the pass fail.
Yeah.
Okay.
So now we need the not equals, right? Which I think actually is just the opposite for us. Like we don't have to do a not equals. It's just like this. This automatically does it for us.
Okay.
I'm pretty sure. We can find out though, quickly. Failed. Maybe not. Panicked at because it's not on. Damn it. Okay, it's not on the curve.
That's not it.
This 6-7 is not on the curve. So what's another point on this curve?
Maybe we can do exercise 1, so we're going to be able to evaluate which of those 4 points are on the curve.
Or on this curve.
Yeah. Which I think is just you just run a bunch of statements creating these points.
Yeah, basically, and see which one fails.
I think he had a clever way of running that. Try to...
In the example he did. So let's see where this one panicked, and that should tell us which was the first one that 2-4 is not on the curve. Okay. Got it. Remove that. Run it again. 5-7 is not on the curve. Cool. So all the rest of these are on the curve. Hey, and our not equals works, actually. I inadvertently tested that as well.
Because it was on the same test.
Yeah.
So when you establish the equal in Rust, it already...
It does the not equals for you, because it's, yeah. Because the not equals is just the opposite of equals, right? So... Okay. Point addition. This point addition. This one was interesting. Because so all right. This
That's how he. So just to illustrate, I found it here. This is what he did to test those 4 points.
we're
Find your. Yeah, stay there. So this is the method he put in. Created like a small function. Just kind of created a little function on curve, and then just returned the elliptic curve equation with
oh
a and
okay, yeah,
b
yeah.
reset, and then just try to generate the same thing, but little clever way with a quick function here.
Yeah, no, that makes sense.
Yeah. Anyway, you were saying?
Oh, the elliptic curve thing. What I didn't quite get was the so every elliptic curve, a line will intersect at either 1 point or 3 points, um, and then it outlines sort of the there's like the exceptions, I guess. There's the vertical line, and then there's this. It's tangent to the curve,
Mm-hmm.
and I guess I couldn't think of any like. I was like, does it really? Will a line always intersect with 3 points on the curve? Um,
Yeah, I thought the same. If you scroll up, like I feel like where is it gonna intersect?
like, what if I put a line up here? You know what I mean?
Exactly. Yeah, it's not vertical, but
Yeah.
where
So that's what I didn't get. Um,
you don't know what's gonna happen with these curves. You know, when they go like really deep, they go all over the place. That's the
that's
thing.
true. Yeah, that's true. Um, 2 points define a line. Since the line must intersect the curve one more time, the third point reflected over the x-exponent is the result. Yep, I remember that. That was one of the videos that I watched. That was like, okay, I get this because there's 3 points. The third point, the third intersection point is where is the result basically.
And there's a nice example in the figure below
Yeah,
of
here it is.
lines.
Yep.
That's a plus b.
But
And
like,
that is like convention, right? That's an arbitrary decision that this is the point addition in elliptic curves. You know, as opposed to something that you derive from calculations and formulas.
yeah, I guess. I wonder. You mean like, yeah? I don't know why it's that way. Is what you're saying? It's like it never gives us that kind of justification.
I think that's like canonical, and he explains why that's addition because of those five uh, properties of addition. Like,
Where's that
let me
at?
find it. I think it's gonna come up. Yeah,
Oh,
there you
these
go.
ones: identity,
Yeah,
community. And this, yeah, this was something that I didn't quite grok when I was reading it. Um, so identity means there's a zero.
yeah,
Oh, okay. So that's just the flipping of the x-axis, right? The I plus a equals a sort of thing, or no? That's a zero.
that would be invertibility, I think.
Yeah, you're right. Yep, invertibility is.
And invertibility is a derivation from identity, because I a plus minus a equals I.
Which I is the is that
Yeah,
the
like this zero.
point at infinity?
Hmm.
Which I don't even want to think about zero and infinity right now, right? Those are some
Yeah.
deep conversations there. This is why we call this point the point at infinity. We have one extra point in the elliptic curve, which makes the vertical line intersects the curve a third time.
Which is interesting. How come this vertical line is not going to intersect the curve anymore? And like until infinity, it's never going to intersect the curve again. But then that line that you mentioned, why that one will?
Yeah, I don't know. And maybe we just can't draw the curve in a big enough shape or something. I don't know.
You know what? You know what? If you draw like a line starting on the x on the positive side of the y,
Yeah.
you know, like kind of going over, kind of like you did. Oh, if I do a line like this, yeah,
Right.
like this, and it just crosses once.
Yeah. That's what I was thinking
But
too.
eventually, like far away, yeah, far away, it's gonna hit it again. I don't know. Yeah,
Yeah, I guess maybe it does.
it'd be interesting to see these curves drawn to
Yeah, that's what I was gonna say. What
very
is
large numbers. Oh, maybe we have that.
Yeah, let's see if we can
MATLAB. There we go.
MATLAB, that is what it is. Oh, no, okay. I don't know. Online plot linear functions. Here's a graphing calculator.
No, no.
So what is it? X um,
Y squared.
equals. That's not squared though. Equals x to the third, right?
Third.
Plus 7.
No, A was 0. No. Oh, that's it. Ah,
Yeah.
because A is 0. Yeah, you're right. Sorry. Oh, there we have it.
Yeah, I don't know, man. I think I could draw a line that only intersects at one time.
Yeah, seems pretty. Doesn't seem that difficult. Yeah.
How do I draw? I don't know how to create a. I don't know the function of a line that would do that though. You know what I mean?
Uh-huh.
Um,
It's like X and Y, right? Like, or
yeah.
2x equals 4y, something like that. Like linear. Yeah. Cool.
Here.
There
This is
you
it.
go.
This is what I was talking about. Yeah. It only intersects the one at one point. Right? But it. Oh, I guess. Okay. All right. Well, no.
I guess then you
So
cannot
I
add.
guess on this line, this line linear function here,
Mm-hmm.
you can't perform addition of any of the points because there is only one point. So you need another point in order to have addition happen. And so in that case, you, you need to have 2 points. So any 2 points on the elliptic curve, right? Because you need 2 points to do the addition. Any of
Mm-hmm.
those 2 points um, will create a line that will then intersect at a third point. Does that make sense? And
Which means
in this case, we have a line that intersects only at one point. You can't do math with just one point. So like you just ignore this line. Like you can't do it.
it's not part of our
Yeah.
universe.
Yeah,
Like
the line is
operating.
irrelevant. The line is just used as an illustration of you have 2 points that you're adding together. Those 2 points will create a line, and that line, because those points are on the elliptic curve, that line will have a third point somewhere that intersects again with the curve.
So the line is a consequence. The line is not the
Yes.
source of what we're
Yes.
doing.
Yes.
And then so there is an infinite number of lines that only intersect at one point, but we
Right.
just don't care about those.
Right, because
Oh,
then you only have 1 point on the curve. We're only doing point addition on the curve, and you need 2 points to do addition. If you only have 1 point, you only have 1 point.
yeah. Okay, yeah.
I think
Yeah, I guess he didn't
Galaxy Blur
clearly
Brain.
like
It just kind of clicked finally.
yeah, he didn't like clearly explain this. So we just don't care about lines that intersect at only
Yeah,
one
hey
point.
Jimmy, go
That's
fix
it.
your book. No, I'm just kidding.
Well, you can submit a pull request.
Maybe yeah. Let me
Yeah,
maybe we should do that. Maybe we should submit a PR.
you're probably asking yourself about the lines.
Yeah, ignore the lines. The lines are a lie, just like the cake. Um,
Okay.
nice. And this makes sense. I did get this when I was reading through how the vertical line only intersects at 2 points, and so the answer is infinity when you're adding those 2 points together. But
Mm-hmm.
there is an infinity point on the curve.
There isn't.
No, I
Like,
thought there is. It's zero,
wait. Hmm.
right? Isn't that what there's a zero
No,
identity?
that's identity.
Yeah, the point at infinity.
Hmm. Which in code we translate to none or null, null in Rust.
Which I was no, there's no null. There's no null in Rust. So that's why
Oh wow.
I don't want to get into that tonight. I'm not ready for that tonight. I was trying to think about how we would make that happen. But we do have these other properties to talk about. So
So
uh,
there's no null in Rust. You can't like declare a variable that's empty.
that's what I was saying. Yeah, there's no null. It's like an intentional decision.
Mm-hmm.
Um,
Wow.
yeah.
Okay. Good luck.
Thanks. Yeah.
Oh,
This is here's a couple of those illustrations where if you have point A and B, you have an intersection at a third point, and then you just
I
inverse that,
never heard it.
which is where it is,
Mm-hmm.
not where it is. This is illustrating the associativity property.
A plus B plus C is the same as A plus B plus C.
Right.
And this is what you were describing that you saw the video with the guy using the cigarette boxes to draw.
Yeah. 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 Yeah.
Oh, nice. Yeah.
Yep. Um,
That's so interesting because it doesn't look like it's going to be the same, but ends up being.
the same. Yeah.
Mm-hmm.
Okay. Let's see. Yeah, I guess, and then the next is just getting into the coding part, which I'm not ready for right now. So.
Yeah, we can wrap probably.
Yeah.
So
Yeah.
does Rust understand like infinite? There is something for infinite. I'm just intrigued. Oh,
I don't know. We can definitely
how
look
to
into
solve
that.
this?
Rust Infinity.
It's like next Marvel movie or something.
Oh, jeez. So there is an infinity replaced by infinity. So there is there's infinity.
Mm.
It's part of this floating point number. Huh. Okay, there we go. I guess we've got our what we can
Infinity and negative infinity. That's
negative.
interesting.
What is negative infinity? That I guess it's just the opposite of infinity.
Which is maybe infinity as well.
I guess we also have this not a number.
Mm.
Um, but I feel like the the truer answer would be infinity.
Yeah, if it has it, because I think he's using none because Python on its side doesn't have infinity.
Yeah.
Yeah, awesome.
First language infinity. So, okay. Well, we'll save that one for next time.
Mm-hmm.
Plublira, thank you again. This is great.
Yeah, this was a great session.
Well, it was really motivating. Like it's nice to have somebody else on the same step and process. So,
Mm-hmm. Yeah, and I feel like we're really digesting these concepts and really understanding them.
I hope so. I hope so.
Yeah,
Um,
I feel like from when we started to now, more and more confident. I was start at the beginning of the session. I was like, yeah, I'll just take it all for granted, code the examples and go forward. Now I feel like I'm starting to actually understand it.
yeah.
Amazing progress.
Well, thanks again, man. And I'm gonna cut the stream here. And thanks for anybody out there in cyberspace watching us in our proof of work programming Bitcoin and
Yeah,
Rust.
invite your friends. Hit
Yes,
us up on Twitter.
yes. We have at Plublira and at Gary Kraus _ our Twitter handles. And yeah, we're just a couple of random dudes on Twitter that happened to meet up. I don't even remember how we met up. How did we? Doesn't matter.
I think you tweeted that you were looking to do this,
Probably.
and your tweet showed up on my timeline. You know when you see a tweet like from 3 days ago,
Yeah,
I think Twitter just knew.
there we go.
Yeah, it's
It knew
awesome.
that you were looking into programming Bitcoin, the algorithm,
Exactly.
the cloud in the sky.
I know.
All right,
They
man.
know everything.
We are going offline now.